year's exam. So I can look at the components. First of all, our exam, as you know, the exam will be face-to-face. Did you guys have any lectures face-to-face at all, or not yet?
Not yet.
Okay, okay. Let me make sure there's no PDF reader here in case the exam opens here. That's here. Uh-oh, that's the wrong one too. Okay, I'll stop sharing my screen for a minute at least, okay? So, exams. This will be covering material roughly from the start of this course all the way until the end. The first important task that we covered was the concurrent forces. So we have to keep an eye on the concurrent forces, one of the first components that you might get a question or two, I'm not 100% sure, a case or two for concurrent forces, okay? Similar, very similar to now let me, since I've got all of those opened, not risking anything, I'll share my screen again. Okay. So similar to this example, this is a concurrent force, correct? For point A. So you might get any of these cases for concurrent forces to start with. That's to cover the first topic. Yeah.
Is it possible I ask you something about it's not about this question, but it's about columns and
today everything is possible. Tell me, is the question particularly about columns or about exams?
No, columns, like columns.
Okay, would you
have some time?
Yeah, definitely. Would you guys be able just to hold it so we can talk about columns at the end? Let me just cover if you want to write down some information, just some.
No, it's not about a question. It's just about like the units, because it's a little bit strange for me. I was
which one is it? Sorry.
It's the columns. The equation, like P equals to P squared E times I divided by L E squared.
Euler's equation. Yep.
Just about it's just about units, because it's a little bit strange. I'll try to okay. When you have some time, just
definitely. All right, we'll go through it. We'll go through it shortly. Okay. I'll just go back quickly to the exams, guys, because we're recording this in case you need to review it when you prepare for your exams. So concurrent forces will be a very important topic that we have to look into. You might get one or two cases, small cases again. Easy one to help you. That's purely really to help you just follow your grades, to calculate reactions and moments. So you might get a beam, cantilever beam, for example, calculate the moments at the support, or you might get a simply supported beam and calculate two reactions. Okay, that's just a very straightforward, easy question. You might get a question about trusses, method of sections. So we agreed, method of joints. It's not part of your exam. Method of sections are. Okay. And did you guys, this is one of the main questions I need to ask you. Did you learn when you guys went through, because that's the lecture, the last, that is the main lecture. where you guys made that transition between face-to-face delivery to online delivery. Can I ask you this? Did you do an example of connection, for example, the shear stress on a port, the tension stress on a plate, the strain in a rod, for example, how much that would elongate? Did you do an example like that? Did you learn how to do those? For example, I'll just show you on your lecture notes.
No, I don't think so.
Okay. Let me just make sure about that. Show you exactly which one I'm talking about. Centroid, center of mass, properties of material. So lecture 8 you got there on your lecture notes. That's before you started with me. These kind of examples, okay, about what will happen when you have an applied, for example, this example here.
Not really, mate.
Fair enough. Fair enough. I'm not going to worry too much about this because I think, anyway, I will cover this probably next semester too, when we teach you the connection details, although that would have been a very good pace for you. That's all good. That's fine. All right then. So we've got that out for a way. What else have we got? Now we'll go to the topics that we did together, which is we've got obviously, definitely you'll have a component to calculate moment of inertia for symmetric shapes again, okay? You won't get any irregular shapes. You will get a question about beams like what we had today. You'll get definitely not more than one case about bending moment diagrams and shear force diagrams. Please, this is a very important topic for you in the future, for me to understand that you guys made sure that you understand how to calculate that. So if we have a beam, how to calculate the reaction forces and how to calculate the bending moment diagrams. Sorry, not to calculate, to draw bending moment diagram and shear force diagram. And from there you can find your maximum moment and maximum shear. So that will be another question. And you will get a question about columns, same what we talked about beams. You'll have another question about columns. And lastly, you might get a question about dynamics, which is we'll cover next lecture. Okay, will be something straightforward and easy to go through. So I think when I went through them, at least I've counted more than 10 questions. Obviously, you're not going to get 10 questions in your exam, okay? I was giving you options of, I'll give you options of questions may go through, okay? And the nature, unfortunately, Benson's asking, do we have any mock exams or previous year's exams? I'm not sure. Is there anything on the student drive? Did you guys check if there's anything? Because I'm not sure. I told you I start teaching this just half of last semester and half of this semester, unfortunately. Let's go to my files. Did you check if there's any previous year questions? Should be some examples there. Regardless, guys, if there is or there's not.
There is nothing on the L drive.
There's nothing on the student drive? Okay. This is student, L drive student. Okay, so if there's nothing, guys, hear me out, please. I guarantee if you just read through the examples that, especially when I was teaching you, the examples that we did in the class, which is all in the recording, you don't have to watch these 6 hours of recording. I'm not asking you to do that, but at least if you go through just skip through to see these examples. The tutorials that I used to send you, either if there was something useful on your actual tutorial booklet, I'll ask you to solve this. For example, for the bending moment diagram, shear force diagrams, I'll ask you to go have a look at your tutorial booklet. So that will be that. For beams and columns, I provided you with enough questions. And for bending moments, shear force, for bending moment and reactions, that's straightforward, really. It could be any of these cases, any beam with two supports or a cantilever beam could be the case. Concurrent forces, I'm sure you've got plenty of examples. If you cover the examples in your tutorial booklet, I'm 100% sure your questions in the exam will be very similar to those. Won't be anything out of that. Trusses, the same thing. If you cover the examples I gave you for trusses, for method of sections, you should be well off to answer the questions in the exam, okay? So in the exam, all I need you, and obviously in the exam will be face-to-face, won't be that much pressure in terms of timing for you, will be very reasonable in timing. Not very reasonable, put it that way. We always design these questions to somehow give advantage for someone who's advanced at this subject, which is fair, will be reasonable. I'm not saying very reasonable. The timing will be reasonable for students. To any student who done the good preparation for the subject will get above average. Okay, that's about the exams. Any questions about that? Yes, Mr. Saberia, what's going on?
Yeah, about the calculator. Are we allowed to have two calculators?
You can have 5 if that will make it quicker.
No, it's just that I got the graphic one, but I'm still not very confident with it. So I also want to my normal
that's
one.
fair enough. That's fine, mate. To me, if it was up to me, honestly, I'm more than happy that you use your phones, because that's what I use these days as a calculator. But unfortunately, we're not allowed to use our phones in the exams. So I'm happy bringing as many calculators as you would like, okay?
All right, thanks.
Shouldn't be a problem. I'm sure there's a point there, Severio. I'm sure by the time of the exam, if you continue practicing your calculator, the graphic one, you should be confident to take it with you. Keep that as a backup calculator just in case.
Okay, thanks.
All good. Anything else, guys, about the exams? Okay, if nothing else, we'll start with Mr. Paolo. You got a question about the Euler's equation, correct? This is our Euler's equation. So asking about the units here. Paolo? Guys, would you like to?
Hello? Yeah.
Yes, I can hear you now. Yes.
So
About the units?
let me get here, just a second.
Easy. Let me stop recording here so we don't have to make this very long.
On that
Actually, keep it anyway. Yeah, sorry, mate. Yeah, I'm with you. Which one?
Question 6. Just don't need to open the question. It's just like.
I've got it here. It's all good. Question 6.
Yeah,
this one. Yep.
Yeah, on this question, yeah.
Mm-hmm.
So we're supposed to have the everything, but the y. So.
What they are what? Sorry.
The y, because sorry, the I the I
value. Okay. Yes.
All the rest we have it.
Yeah.
So can you get back to the equation, please?
Yes. That will be here. Yep.
Yeah. So the P, it is a force. So the unit is Newton or kilonewton. It doesn't matter.
Let's keep it uniform. Newtons. Yep.
Yeah. The P, pi. There's no unit.
Unitless, correct.
Yeah. The E,
Yep.
is in megapascal, so we can write as Newton per millimeter squared.
Correct. So let's write them down. We've got newtons, Newton millimeter squared. Yep.
So
In fact, I'll write it this way, Paolo, so you can follow up with me. Because this is a Newton per millimeter square.
yeah, you can put on, then no worries. Okay,
So I'll put it here.
can put down as well.
Square. Yep.
So the LE squared should be L times unitless. I think it's like this. So it after you squared will be millimeters squared as
Square.
well.
Perfect.
And the I
Yes.
should be millimeters to the power 4.
Correct. Can you see my screen?
Yes.
Okay. So does it make sense? Look at it.
Yes, but
This, that will give you newtons.
when because I put all the numbers,
Yes.
we had to find millimeters at the answer of T. And for some reason, I couldn't find millimeters.
Yeah. Okay. Look, for that form of the question, first of all, the units for the formula is correct, right? From here, that's correct. Agree?
Yeah, I agree.
Okay. Now let's go back to our question. Rather than having millimeter to the power of 4, let's define this. How does it come? I value. I think the I value for a circular section will be pi d to the power
Yeah,
of
because
3.
this is to the power of 4, right?
Yes.
So the answer will be millimeters
Yeah.
to the millimeters to the power of 4. But if you take the square root of, not square root, but the square of 4, root of 4, you can get millimeters.
Yeah.
Okay.
So, you're good. Did that answer your question? Or not?
Yeah, because I was doing the question every time I cancel all the units, and
Yeah.
the D was unitless, and I was like without understanding, because I know the units, but for a reason, yeah. But was my
Okay.
mistake
So
as well.
just so we can be clear. Okay, guys, that's a good legitimate question for any one of you might ask that question. So we can be clear for the future. I will never ever ask you to memorize in this formula. I have to use this in that formula, because you will come across lots of formulas as we go forward, especially in the next semester. Okay, when we start talking about the calculation for reinforcement in a concrete beam, you have one large part of the equation, including the area of steel there, including the FYS, which is the strength of the steel, the depth of the beam in millimeters, the depth of concrete in millimeters, the width of the beam in millimeters, the strength of concrete in F-C, in, again, MBA, Newton millimeter square. So you got lots of components all in one formula, and some of them they went to the power of 3, to the power of 4. All of this could be to the square, not square, the cubic root, so to the power of 1 and 3. All I'm asking you, long story short, just so I can make it much easier for you, all I'm asking you, please, if you want, or if you need to memorize anything, memorize how can you make your units uniform. That's all I've been saying since the start. If I'm using MBA, I have to make sure with it I'm using newtons and millimeters. Okay, sorry, that's millimeters, not meters. Okay, if I'm using KBA at the start, when we assigning the actual loads, how much the weight of the floor, how much the weight of people, the wind, pressure, all of those would be more in KBA, kilopascals. If I'm using kilopascals, I have to start thinking of kilonewtons rather than newtons. Let me just write it properly. Kilonewtons and meters rather than millimeters. Okay, these these units will correlate with each other. What else have we got there? I think I've got a slide there just showing you a few things about the units. If I have things, you'll come across things in kilograms. Like in this example, I think you have the weight in kilograms. What is the unit that I can change from kilograms, guys? Can anyone tell me?
Newton.
So
No.
9.81.
So if I have, let's say, 10 kilograms, what should I do, Ina?
So we should, with the gravity, so 9.8 kilograms.
So, yeah, what should I do that? 10.
10
Mm-hmm.
multiply and 9.81
Mm-hmm.
and so,
So-
kilogram meter per sec square.
So, kilograms, to change it to kilonewtons, first of all, the newtons to newtons to kilograms multiplied by 891. But kilograms to kilonewtons, I have to divide by 1,000 then. Okay, that will change to newtons and then divide by 1,000. Okay, or because that's always, look at it, this format here, always fixed. If I need to change kilograms to kilonewtons, what I can do, simply, I can divide by, kilograms to kilonewtons quickly. So that's something you can memorize. This is something I do it myself. It's not in your book. I find it easier because most of the cases we change from kilograms to kilonewtons. If I need to change to kilonewtons, all I have to do, divide by 1 or divide by 1 or 1.9, which is the answer of this. If you divide 9.81 divided by 1,000, that will give you 1 or 1.9. So 10 kilograms divided by 1 or 1.9, for example. What do we have? 10 divided by 1 or 1.9, and that will give me straight away 0.98. 0.098 kilonewtons. Always think about it this way. It's almost 0.1. Think about it this way, how to memorize it, guys. Why do you need to memorize this 1 or 1.9? Each 100 kilograms is roughly 1 kilonewton. Okay? So that would be the answer here. Don't forget, the answer here would be in kilonewton. If I need to change from kilograms to kilonewton. Think about it, roughly 100 kilograms roughly equals 1 kilonewton. When you start thinking, that will be easier for you just down the track as engineers to start thinking, how much should I allow for the weight of insulation inside the floor, for example. I need to start thinking about that when I'm designing the beam supporting the floor above it. How much should I allow for the insulation? It's always easier for us because we use kilograms on regular basis. Kilonewton is more force and engineering unit. It's easier for us to visualize things in kilogram. You can say, well, if I allow up to 10 kilograms per square meter, that will be enough for that. So straight away, I've got that idea in my head. I change it to kilonewtons by dividing by 1 or 1.9. That will give me kilonewton. Okay. How much the weight of people, for example, standing on the floor? I would say, well, one of the worst case scenario that 2 people are standing together within 1 square meter. If I'm trying to work out live load in a house, for example, I would say maybe 2 people are standing together. Well, 2 people if you would say two people, each one of these people is 100 kilograms, you are a bit maybe overestimating, because not everyone like me, 100 kilograms. You got people 60, 70, 80 roughly. So if we say two people, yes, safety will comes after. I'm answering Manav, by the way, he's sending comments. He's saying for safety. Safety will come after, Manav. We will apply safety factors after, but as an initial estimation for houses, we assume, let's say roughly about 150 kilograms, two people standing together within 1 square meter, because it's very highly unlikely. Imagine there is a floor, in every square meter there's two people. Unless you are in a concert or something like that, very highly unlikely for that to happen. Correct? So therefore, for a residential project, it will be very safe to say 1.5 kPa. That's from the Australian standard. Let's try to understand what 1.5 kPa equals to 1.5 kilonewton per meter square. Let's make this more sense to us. Roughly, I would say roughly, about 150 kilograms per meter square. Okay? So we will talk about those a bit more next semester, all of those. I'm trying just to brief you into them. Generally speaking, the most important part for me, always keep your units uniform, please. That's all. If we are trying to get an answer in millimeter, and this will need some logical thinking from you too, right? For example, if I'm designing, that's one part of the designs that we talked about, beams and columns in general this semester, but next semester we'll start designing those in details. If I have a beam spanning between 2 points, the span in say 6 meters. You see, when I'm talking about the span, I can say 6 meters easy. But when I start thinking how much the beam will deflection, that means how much will it go down here, bend, that distance, that's usually a very small distance. It's not very logical to describe that distance in meters. So that's why deflection will be in millimeters, okay? So your judgment will be made, long story short, your judgment will be made, what unit do I desire in the answer? Do I need the answer in meters, millimeters, newtons, kilonewtons? Based on that, adjust your units within the formula to be uniform. That's all I'm asking you. All these units are designed in a way, there's no really rocket science there. All these formulas designed in a way that the units are uniform, that's all. As long as you use the right units that will correlate together. If I'm using megapascals, I'll use Newton millimeters, gigapascals, change it to megapascals, and change all the forces in newtons, distances in millimeters, then you can get your answer. If you are after the distance or deflection, you'll get it in millimeters. If you're after force, you'll get it in newtons, like in our case here. Okay? This is the secret. That's the only one way that you need to know about it. Other than that, because I gave you an example before, didn't I? Like, just to remind you, like for calculating deflection, which is we looked at the dice briefly, for a simply supported beam, 5WL to the power of 4 divided by 384 times E times I. So if you try to, W could be in kilonewton per meter, could be kilonewton per millimeter, Newton per millimeter, L could be in meters, millimeters, E, GBA, KBA, MBA, I, millimeter to the power of 4. So if you are really going to try to think through it too much and make your units cancel each other, that will take for a very long time. All I'm asking you, any of these formulas will be 100%, will work 100% correct if your units are uniform. So I want deflection in millimeter. That means let's keep everything in newtons and millimeters. I know these works well together. And MBA. Sorry, W, I'll make it in newtons. Sorry. Length, I'll make it, although length for the beam, that's the span of the beam, usually described in meters, but so I can get the right answer, I have to put it here in millimeters. Okay, so it'll be millimeter to the power of 4 overall. And I've got E, which is, again, I'll choose MBA, in other words, Newton per millimeter square, I millimeter to the power of 4. Okay, 5W to the power of 4 EI, newtons, millimeters. What would that produce for us? This is doing my head now. What would that produce for us? 5W to the power of 4. Yep, so that's in millimeter to the power of 4 would be all together, which is really 5WL times L to the power of 3, doesn't matter. And 384E in Newton per millimeter square, I millimeter to the power of 4. These will cancel each other. Newton and Newton will cancel each other. This is a constant number.
We got millimeter square.
I know. Doesn't make sense. Now this is okay. Let me just see where.
The E should be in gigapascal, I think, because I was trying to do the exercise and I always have my answers incorrect. And when I tried to see some exercise in the internet, they was using gigapascal for E. So this was my questions about the whole exercise. I got the wrong answers because I was using megapascal.
Let's double check that. I'm almost confident it's megapascals, almost. Let's check that because I've done it like trillions of times.
I actually checked. Sorry, Aaron.
You're right.
I actually checked about
it's a good
the E.
discussion. Sorry, yeah, I'm with you.
About the megapascal, and it actually worked for me.
Yeah, no, it should work for megapascals. Let me check quickly for you guys, just see where the thing here. Lecture notes or steel lecture for the second one in deflection. We go. We looked at those, I think, last week. That's why we're here. There we go. 5W to 4 EI, 384 EI. No, just should be correct. Just checking in case I made a mistake there. Let me show you an example just to make sure we're on the same page. Stella. And actually, that's a good point. I'll look into it. And no, there must be something that I can't see here for any reason. Where are we? If we go to lecture notes and deflection, we'll learn it probably. And solution, for example. Okay. So look at that. All our answers, which is you'll have the next semester. For this beam, for example, if I'm trying to calculate the deflection from the UDL, I don't care about the point load. That's in millimeter. That's what that PLR, that's for the, don't worry about it, that's for the point load. Now, hold on a second, guys. I made a mistake here. Newton, yes, W here, guys, I forgot. W, we never describe it just 5. When we say W, that's a uniform UDL. correct? So UDL, never describe it in a Newton. Have you ever seen a UDL in Newton? Newton per millimeter, for example, or kilonewton per meter, which is exactly the same. So this is Newton per millimeter here. I forgot that. Okay? Make sense? W, never in newtons. For some reason, I put it as a point load in newtons. In W, when I give you a beam, that was a shock in the morning. You guys made me rethink my calculations for the last 10 years of engineering. They all should be wrong based on what we came up with today. So if I say I've got a UDL W equals to 5 kilonewton per meter. In other words, this is equivalent to 5 Newton per millimeter. I'll change, this is divided by 1,000, this is multiplied by 1,000, this is multiplied by 1,000, will give me the same, will cancel each other. So my units here, Newton millimeter, Newton per millimeter, millimeter power 4, millimeter power 4, Newton millimeter square. Okay, Stella, always use it in MBA. Again, you see, without me even thinking why we're using this and that, if you notice, if let's say I'm doing the calculations, without me overthinking things like what we did today, I used the right numbers here and I could have got the right answer if I put the numbers in place without even thinking of the units. Why? Because simply I know the units should be uniform, that's all. So you can't use GPA, Stella. It's not good to use GPA, or it's not good. We'll give you, it should in theory give you a wrong answer if you use GPA with millimeters and your forces in newtons or Newton per millimeter. All good?
Yes, I just didn't got the same answers, but we can see when you got through the exercise.
Yep. All right. We'll do that today. Okay. Anyway, the question, the point I was trying to make here, that just take my advice, and I told you it's worth, guys. You trust what I'm telling you for some time until you get used to it. Take my advice. Keep your units uniform. That's all you need to do. Keep an eye on these two expressions there. They are very useful. MBA using Newton millimeters, KBA using kilonewton meters, and obviously that will follow kilonewton meters, meter square if I need to use meter square for area, millimeter square for area. All what we're saying, anything for measuring lengths would be in millimeters for when we're using MBA, and in meters when we're using KBA. If that's it's up to you if you want to do it this way. If you want to change from kilograms to kilonewtons, divide by 1 or 1.9, which is the product of this. Otherwise, if you would like, it's easier for you, multiply by 9.81, divide by 1,000, that will give you the answer in kilonewtons. If you multiply, what Hannah said is correct, that if you multiply by 9.81, that will give you the answer in newtons, not kilonewtons, in newtons. This is to answer the question about units. Any other questions about units?
No, let's start the exercise.
Okay,
I have
that's
so
it.
much questions.
All right then, let's do that. So I start with, I will close that for a minute. Actually, keep it for now. This is the one. We start from question 6.
Yes, please.
Yep, easy done. Copy, and let's go there. All right, guys. So it's asking us that there's a load of, in the question, I think it says there's a load of 5 kilograms mass. You see, when we say mass, kilograms, that means we have to change it to kilogram force or sorry, which is kilogram force, or we can change it to kilonewtons. That's what we work with, kilonewtons. Determine the required minimum diameter for the solid steel rod. So this is a rod, the cross section is circular, and it's solid to the nearest millimeter, so it will not buckle, so we can avoid the buckling. So I've used the factor of safety 2 against buckling. Yielding stress of the steel is 250 MBI. Okay, so FSY is 250 MBI. That's to give us if we are within the margins or outside the margins of Euler's equation. But let's start with this one. So I've got 500 kilograms here. Straight away, I'll think through it. I told you what I usually do. 500 divided 101.9. Yes.
What is this welding stress?
Sorry, say it again, please.
What is the meaning of yielding stress, which is 250
Okay, so FSY, yep, that's fine. FSY, what we call it, which is the yield stress of the steel. Do you remember what I told you? Euler's equation applies. This is the stress strain of a steel bar. May go hardening wherever. Okay, it doesn't go down. Goes straight like this, and then strain hardening, and then fades. Done. Okay, so at this point here, we call it the elastic part, where the relationship between stress and strain is linear. By increasing the stress, the strain will be increased. Strain is simply if I'm pulling on this, look at it, if we add more weight, this will shorten a bit more, will shorten slightly. We're talking about, you've seen it in the video, few parts sometimes, or parts of millimeters, sometimes just few millimeters, depends on the size. And if I add the weight, this will shorten more, or the other way around. If I pull a steel part, that will be elongated. This part here, guys, this part here, elastic part, we call it, okay? This small portion here will stop being linear if this continued linear like this. Will stop being linear, we call it non-linear portion, this area here. Still within the elastic, but stop being linear, in a linear relationship. Not very important to you. The important part for you is this point here. That's what we call it Fy. When we say FSY, that means the yield stress of the steel. So if I know this is 250 MBA, that means if I calculate my, you remember the slenderness ratio, the table of the slenderness ratio, or lecture?
Yes.
Yes, so I have to make sure which ratio I should choose. This one here. See, so if I'm talking about the 250 MBA, it would be more related to this type of steel rather than type of steel. So this is my ratio, my slenderness ratio should be in. But if I was talking, for example, about 450 or 350 MBA, I have a wider range that Euler's equation will apply in it. Okay, that's all what this is all about. And I told you, please, for this particular tutorials, because these numbers, I didn't go through them to check, are they correlating with this table? Don't worry too much about the slenderness ratio to be within these two elements. In the exam, I'll make sure the question, if we will have questions about columns, I'll make sure the question, when you do the slenderness ratio, should fall within right components in the exam. But for the tutorial purpose, I didn't check them all. And I told you I got some of those from different books, and they may have different references there. So that's the reason for it. Did it make sense? So just to tell us here, which part of the table I should look at, this row or that row?
That's okay, thank you.
All good? No worries. Okay. So Let's go back to our question. It's asking me that you've got a 500 kilograms load. Again, I'll just redo it again based on what we discussed just before this. Straight away, I think 500 kilograms is not useful to me. What would be more useful? Kilonewtons. So 500 divided by 1 or 1.9, the number I gave you. That would be equal to 4906. And that will give me, I'll say here 4.9, let's say 1 kilonewton, okay, just to make it easier. 2 decimal digits should do the job. Okay, now I'm looking at joint A. I've got concurrent forces example, one of these things that were done many times in trusses and in concurrent forces at the start. I've got 4.91 kilonewtons applied here. I've got a force there, roughly about here, another force here. I don't know these forces yet, correct? So I'll assume these forces tension. That's what we agreed on. All I know, I'll call this one P because that's what we will try to find, okay? And I'll call this one, let's call them F1, F2, just so I don't get confused with anything. F1 and F2. Which one do I need to find, guys? I need to find this force here, which is F2. That's the important part for me. That's what we're looking at. Let's find out the angles. If I've got this angle here, 60 degree. Look at that. If I continue this triangle here, that's 90 degrees. This is 60, that will make this 130. And the same thing if I continue this triangle here. This is 90 degrees. This is 45, that means this is 45. All of this will make 90 degrees. I've got 30, 45 in between them. How much do we have? 45, 35, 75 to 90, that will be 15 degrees. So all what I'm after, just to write down that I've got here. So this is a bit too large. It's not really good representation. I'll delete that. This is at 30 degrees that way. F2 we called it. And this is 30 degrees. And I've got another small angle here. That. And we call this F1. This is 15. And this is 45. So, do you remember the tips that I gave you when we have concurrent forces? As we said, we always have standard cases, not standard, like more repetitive cases that we usually come across. And this is one of the common cases that I have one known force, two unknowns. Anyone can suggest what should I do?
We take the moment around D.
We take a moment around D. Yeah.
And we should be able to find the force AB.
Because you are saying, if I take a moment, you're looking at this as a truss. If I take a moment around D, this force here will be by that distance, which is I have to calculate 4 by cosine 60. That is the distance for that. And this is concurrent force. I don't worry about it. This is the only one force, but then you have to find this distance here, or you'll take the two components of that. Is that correct? Is that what you're doing?
Yeah, we can easily find the sides of those triangles.
Mm-hmm.
And then we have the distance from point D for each force.
That's one way. Any other ways, guys?
Can we rotate it?
Perfect. Who's that?
Benson.
Benson. So when you say rotate, can you please clarify what do you mean by rotate? Let me just clear that for you quickly. When you say rotate, what do you mean by rotating? I'm listening, mate.
Rotate 45 degree.
Perfect. What Benson is saying, which is I find it personally slightly easier, or what Severio said is 100% still very easy, honestly, which is a great way of thinking of it as a truss, work 100%. But what Benson is saying for concurrent forces, if we have, this is our X, and this is X, and that's Y, let's draw a new, let's rotate dice by 45 degrees. Why 45 degrees? So we can have one of the forces on the neutral axis, so we can eliminate that force. So in other words, if I draw another axis like this, I'll just do them in yellow. We'll call this X, for example, and then 90 degree on that. Roughly here, that will be Y. Well, what we're doing, guys, really, all of this, you don't need to draw all of that. I'm just drawing it to explain it to you. So what we're saying here, this will be X dash, we call it, and Y dash. Look at it now. If I take sigma Fy, this force, the problem initially, by the way, our main problem to start with, that we have two unknowns. We have two equations initially. Just clean this. So we said this is, I think, was 30 degrees, it's 15 degrees, and this is 45 degrees. So our major problem, guys, that we have two equations and two unknowns. Two equations, which is sigma Fy equals to 0 and sigma Fx equals to 0. These are the two equations that we usually use for concurrent forces. I have two forces unknown. I have to eliminate one of them. By rotating my axis to make one of the unknown forces on one of these axes, since I know all the angles, by rotating just 45 degrees, look at that, X was here. I flipped it, moved it here, look at it, moved it here. That's X here. Moved it 45 degrees to be on this line. That's all I did. So that means this angle here is 45 degrees. Because Y was here and I moved it by 45 degrees. Now by doing this, I can easily say sigma Fy dash equals to 0. Look at it, this is completely gone. F1 will be 0 on the Y. The only one thing I've got is F2 by cosine 75, or I can say sine 15, wherever is easier for you. That's acting downward, so negative. What do we have? F2 times cosine 75. That's there. And I've got 4.91 by cosine 45. And the same going negative, the same direction. Negative 4.91 times cosine 45. This equals to 0. This equals to 0, that means F2 equals to that divided by cosine 75. Obviously, this will be positive when I move it. Let me write it down. So it will be all of this positive after I move to the other side. So it will be 4.91 times cosine 45 divided by negative cosine 75, and that will equal to sorry 4.91 times cosine 45 divided by negative cosine 75. That will be negative 13.41. Negative 13.41 kilonewton. What does that mean, negative? Can anyone tell me?
It is in compression.
Exactly. So we assume the force in tension. That means the force is the opposite direction in compression, which is to us really is not very important at this point. Or we're saying the force, it doesn't matter for us tension, like we know it's going to be in compression. So we can say F2 equals to 13.41 kilonewton in compression. Is that the same answer you got there, Severio, with your method?
Yes.
Okay, good. So we got that to start with. Now we go back to our column problem, which is we know the force, I know the member, I know the length of the member. I can almost estimate everything on it. Let's write our equation to understand what's going on. So P agreed on the buckling load equals to pi, just had that, L to the power of 4, pi square, EI. See, even me, I don't memorize it. This is one of the formats that we don't really use too much in actual structural engineering. It's called like the Euler's equation applies in limited areas. That's why we don't use it. But anyway, as I said, you don't need to memorize formulas. EI on LE square. I think this pi square was. Yep. Okay. In theory, to start with, we have to check first of all if our LE on R is within the right range. I told you for this particular examples, may be within, may not be. I'm not being too fussed about it, but in the exam, please do that. So you've got, I will ask you specifically, check if Euler's equation will apply. So first of all, to know if we can apply this, we have to check the slenderness ratio, LE on R, should be in the right range. LE will equal to K times L, or for a column. R is square root of I on A. We need to find the value of K, I, and A. Sorry guys, I know some of you are well advanced in those, but I'm trying to recap on those for everyone. Okay, so we can all move at the same rate. K, if we go back to our lecture, is the effective length factor from this table. Let's look at the example. We have a pin. Why do I know pin? Because I know I can tell from here, this member AB can rotate here and can rotate there. Nothing stopping it from rotating. It's not welded, for example. It's a pin support. So I've got pin. This is my case. Where is it? This is my case. That means KE equals to 1. So I've got the value for K. That's 1. L, here's the question. What shall I write? 4 or shall I write 4,000? Suggestions?
4,000.
Perfect. Thanks to everyone. Again, all what we're trying to do is just keep them uniform. I've got I in millimeter power 4, area in millimeter square, area of the section. So let's keep everything in millimeters. So I've got that in millimeter. the I value for a circular section. I value, that's there, I for circular section. Obviously, there's no IXX and IYY, guys, for circular section. Look at it. In all directions is the same. Doesn't vary. It's the I value by d to the power of 4 on 64, I think. That's to memory.
I got a different formula.
Why is it?
I got over 4, not 64.
By d squared to the power of, or is it r squared?
R to the power of 4.
Okay. So, sorry, d to the power of 4. I miswritten this. It's to the power of 4. So it's the same.
Ah, it's the same.
Yeah, because I can write d is r on 2 to the power of 4. So it will be d to the power of 4. So what's your formula there? If you do them, you'll find them the same superior.
Yeah, that's what I found. Pi over 4 times r to the power of 4.
Yeah, because we are asking about diameter, I prefer to keep it in diameter.
Okay.
Because the question is asking about diameter, or you can calculate in radius, the same. As I said, this is, by the way, to start with, this is a new lecture notes. Again, I think in the same lecture here. Properties of material, I values should be at the start of this lecture. We've got at least a few different shapes, the triangle, rectangle, and circle. To memory, you've got them there. That's the torsion. You guys have the lecture notes, don't you? The centroid lecture. So I'm just looking at your lecture notebook. The centroid and center of gravity, center of mass. You've got 3 formulas there. So calculating the centroid. There we go. These are the 3 formulas you've got there, guys, for moment of inertia. So pH cube on 12 for rectangle. Depends which one is H, which one is B. Always we agreed B is parallel to the axis that you're considering. For a circle, it's the same in both direction, and that will give you pi d to the power 4 on 64. Okay. For triangle, when we have it going through the centroid, which should be in theory in the third of the height of that triangle, that will be b h cubed on 36. H would be the height, b is the width of the base. Okay. So you've got those in your lecture notes. Anyway, if you don't, just write this one down for circular. Anyway, focus on the rectangular. Mainly is the main I value you need. Circular is used too. Okay. So I've got the formula for I, and I need, obviously these are known for us, so we'll keep it as is for now. But I've got the area, the same thing, by d square on 4. That's the area for a circle. When I'm writing d diameter, okay, you can just, if you prefer that way, you can make it larger, d. So if I try to find the radius of duration, r equals to square root of, what do we have, pi d to the power 4 times 4. That will come from the top, from bottom up. That will be there, divided by d square multiplied by 64. So we can start cancelling each things together. I've got this will be cancelled with that, we'll leave just d square at the top. Pi will be cancelling each other. And we've got for the 4, 64 and 4, so altogether that will be r will equal to pi is gone, d square, as we agreed will be 16, d4 and 16. And if you, the square root of that, r will equals to d on 4. All good? What do you reckon? You guys got the same answer for the r value, or you didn't check your r value?
It was the same.
Okay, good. So we found our r value, our LE value, we found it there. LE is 4,000. LE on R, 4,000 on times 4 on G, and that will be, so what do we have here? The slenderness ratio is really still in relationship to D. Okay, that's fine. We'll check it at the end. So we've got 16,000 on D. That's our slenderness ratio. Let's keep it on the side. We'll check it at the end if it will be within the right range. As I said, this is not really applicable to all questions, but we will do that check anyway. So in terms of finding the buckling load, and the question is asking us for a safety factor of 2. So in theory, you could have, if you would like, you could have just multiplied this load by 2 straight away from here. That way you got your safety factor by 2. Or from what we calculated in the force applied in this column or this member AB is 13.41. So in theory, we want our member P to be 13.41 times 2. And that would be 2, 26.82. kilonewton. Okay, that's it. We've got all the components, I think, for our equation. So this is our equation. Don't forget, this is what we're trying to work out. We found the value of I, it's here. All what we have to do now, just put it all together in the formula. Okay. So we've got P value is 26.82. That's kilonewton. I want things to be in millimeters. That means I have to make this in newtons. Times 10 to the power of 3. I'll change it to newtons, equals to pi square times E in megapascals, always for millimeters and newtons. So it'll be 200 times 10 to the power of 3 times I. This is the value of I, so I'll just put it here again, pi d to the power of 4, all divided by 64. I'll put it here at the bottom straight away, multiplied by LE, which is 4,000 millimeters to the power of square. Look at this, guys. Everything is known. The only unknown is D. And again, just easier to have those in your calculator. You can rearrange things, or you can just enter. So D would be the 64 by 4,000 by this number divided by those, all of this to the power of 1 on 4. if you like to do it that way. So I'll do it just with the calculator that you have solver in it quickly, and we'll do it for the other calculator. We'll see the answers. So I'll write straight away 26.8, actually without points, 26.820. That's multiplied by 10 to the power of 3 equals, I've got pi cubed, so that would be shift pi cubed times 200,000 times x divided by 64 times 4,000.
You type at 60 instead 64.
Thank you. Thanks. You got me just before 64, and there'll be then shift solve, and that will give you, okay, 44. There's, seeing this, there's an issue with the units. So what do we have here? 200 megapascals. That's in megapascals. Pi to the power of diameter. We've got it. The diameter. Yeah, we need it in power 4. No, that's where the problem is.
Just a question. Why you put a pi?
Sorry, I forgot to put here to the power of 4, guys. That's where the problem is. D to the power of 4. That's all. Yeah. So say it again. Who's asking?
Sorry. Why you put pi square rather than pi cube? Sorry, pi cube instead of pi 2. Pi
Cubed.
Yeah.
Because I've got pi here and pi here. I thought it was just easier for me rather than
Okay.
twice.
Yeah, it's okay. Thank you.
Okay, no worries. So I shift solve, and that gave me 51.42. Did you guys get similar answer? That's slightly different than what we got there. So let's try that. D equals to 51.42 millimeter. So that's the minimum will require.
I got 46.
I'm listening. Sorry, what did you say? You got the 46 answer?
Yes.
Fair enough. Let's see where our differences are. So this could be a difference now. What did you use your buckling load? Did you have exactly 26.82?
Yes.
Hi, Aaron.
Yes.
Yeah, I'm so confusing because, and you said that one is 200 times 10 power of 3, right?
That's right.
But in the lecture notes, we have to write down 200 times 10 power of 9.
200 times 10 to the power of 9?
Yes.
Well, how come? Newton, if we need this in Newton millimeter square, MVA, times 10 to the power of 3. Just, sorry, that's 200 to the power of 3. That will make it MVA, which is Newton per millimeter square. It's 200 GPa to make it. It's the value of E, guys, is 200 gigapascal. 200 gigapascals. Where does it say in the lecture notes? So the value of E, 200 gigapascals. If I need to use it with the units to be uniform, they have to be 200 times 10 to the power of 3. That will be megapascal, and that should do the job. And like,
This was my initial question because I saw some exercise in the internet, and there was, especially in the YouTube, they was explain how to solve the problems, and in the all examples they use 200 in the 10 of the power of 9.
if let's say I'll put here to the power of 9, just so I can go with you, okay? So that would be another 3 zeros. What do you mean? Why more than that? So, guys, keep an eye. Did they use at the bottom? Did they use meter? If they used meter, that's why. I'm using millimeter at the bottom here. So anyway, I'll just go by what you're saying. 200 times 10 to the power of 9. Shift, solve. You see that will be completely wrong answer. 1.45 millimeters. So what could have done, just for you to know, guys, what they may have done, they've used meter here. They have used meter in here. 2682. Yes, Manal, I'm using kilonewton. I'm using this in newtons. But anyway, just to answer you, what could be the thing for you, what you see on the internet? That's why just try to let's be more academic about it and scientific about it rather than just on YouTube. We have to keep our units uniform. If I use the meter, that means they're changing the meter to millimeter times 10 to the power of 3. Or are they changing this to kilonewton per meter square? So it just could be, on these examples, Stella, you've seen, did they use meter or millimeter at the bottom?
Yeah, now I got confused. Maybe they are using meter.
Okay, just trust me. I've done this formula with the elastic modulus, lengths, forces, hundreds and hundreds.
Yes, I believe you.
Okay, so if we're using millimeter, use MBA. Anyway, 51.42. I'm just checking where the error is. It could be just some, marginal error on the accuracy. That's all. So what do we have here? 26.82. Is that the same force you guys used there? Just check what I've entered here for that. And if I'll go back to our 1, 2, 3, pi to power 3, just checking our I value divided by 6.4.
I think, Aaron, well, some of us were looking some videos on YouTube, I think, and there are also some books on internet that said there are some difference between the effective length factor and also using meter rather than millimeter. So maybe that's why some of us are confused with the measure, because if we use to the power of 9 rather than to the power of 3, we maybe can get the answers from the question 6, which is 46 millimeter.
Show me. So I'm happy to take that. Which one shall I change to get that answer based on the numbers I've got here?
For example, 200 times 10 to the power of 3. That one should be to the power of 9, I reckon, I think.
Okay, I just did that. Did you see when I did it? So if I say 200 times 10 to the power of 9,
yep,
that's what you're saying, correct?
Yeah.
And if I solve for, what else?
Let me check. I can share you if you want the video. I have to look for it. I don't have it now, but I can share you in a minute if you want.
Look, feel free to do that, but I think based on the numbers that I've got here, I'm confident these numbers should be the right units here.
Yeah, the main difference is when we use millimeter and meter, but yeah, basically, I think, it's okay what you're doing, basically, yeah. I'm not...
No, let's look, guys, I even love it when you guys challenge me. I'm more than happy to do that. All I'm saying is I'm confident about what I'm telling you here. If all what I'm asking you, keep your units uniform, that's all. If you are using here, let me show you, I think it's just about the accuracy. For example, let me show you this. If you are using meters in here, that will be different. That will be different. Then you have to make your units uniform to, and you'll get your answer in meters. And that's what I don't want to have. If we need our answer in millimeters, I have to use anything megapascal, kilopascal, gigapascal. I have to use it in megapascal because it's Newton per millimeter square, because my desirable answer to be in millimeters. Okay, if you need your answer in meters, I'll tell you, yep, go ahead and use kilopascals, for example, if you have kilonewtons there. That's what you're doing. 200 times 10 to the power of 9, that'll be in kilopascals rather than megapascals. Whereas what I'm telling you here, we need our answer in millimeters. So the E value, the elastic modulus, should be in megapascal. So I can get straight away my answer in millimeters. And all I'm saying, my answer here, I'm certain it's correct. 51 to 46 is very easy rounded number. Could be just one of these numbers slightly off modified, because the only one number, it could be this. Let's try, for example, rather than 26.82, which is, look how much I rounded my numbers. This was, if you remember, this was 13.409 or 05 or something like that. I made it 13.41. So I rounded this number. Let's make this number, for example, 26.8. Just so I'm certain this is just about accuracy of this number, which is in the exam. I will assume I'll give you full marks for getting an answer like this. What you did there, you took a slightly more conservative approach rather than saying 13.409, whatever was the answer for it. I'll check exactly what our answer was. In a minute, I'll check, but I don't want to lose what I've entered here. So let me clear this, 200,000. Let's say, for example, that rather than having this, I'll have it 0.8, 26,800. So all I did, just modified my accuracy. Rather than taking 26.82, I took 26.8 times 10 to the power of 3. That will be that. Shift solve. And that's, there we go. That's 45.86. That's 46 millimeters. That's the exact answer you got there. So just by having that A2, that changed my diameter to 51. Why? Because why I got a slightly larger diameter? Because I was initially from here. Let's go back to our calculations. Guys, are you with me? Do you mind if I ask you stop writing for a minute? You've got all of this recorded anyway. Let's just get the thinking behind it. If I go back to my calculations, I did erase them. Let's go back to this calculation here, which is 4.91 times, by the way, 4.91 is still conservative too. If I do it exactly rather than 4.91, which is 500 times 9.81 divided by 1000, that will give slightly less than 4.91. But the formula I gave you will give you slightly more larger number, which is more safe, conservative. Okay, we've got that. Now, all of this multiplied by cosine times cosine 45 divided by, I will ignore the negative sign because it just will tell us it's in compression, divided by cosine 75. 13.4 rather than 13.41. So that will change here. Our 13.4 kilonewton. Okay, perfect. Now multiplied by 2, that will be 26.8. If I solve this for, so I'll write it here if you'd like, 26.8 kilonewton. If I solve this without the 2, which is for 26.8 times 10 to the power of 3, and please, I'm confident those are the correct units there. let's just solve this again so you can see it. If I do that, here we start from 26,800, which is 26.8 times 10 to the power of 3 in newtons, because that will work better for MBA and will work better for millimeters. Equals, what do we have? Pi to the power of 3, shift pi to the power of 3. Pi to the power of 3, I've got 1 pi here, another one there, times 10, 200, 1,000, 1, 2, 3, times x to the power of 4, nope, wrong one, shift x to the power of 4, divided all by 64 times 4,000 square. Shift solve, and that gave you 45.86 millimeters. So diameter 45.86, and the question is asking you to the nearest millimeter equals 46 millimeter. Okay, so you understand, guys, when I'm initially calculating from this point onward, I'm always, if I get a number 30, you've seen it, 13.409, I take it 13.41, just slightly larger, because I know that will make me safer. And continuing doing this way, multiplying that safety by 2, solving the equation to the power of 4, that gave me a few millimeters larger. So that gave me, if I'm the engineer, I'm designing this, I'll tell my client, your minimum diameter will be 52 millimeters, which is slightly safer number than calculating numbers just on the edge there. That's all what it is. All good? So let's go back for this equation. We got B equals to pi square E I on LE square. Please, if I need to calculate if I need for any reason a number in millimeters or without that, because I've got MBA here, just straight away use this in MBA, 200 times 10 to the power of 3. By the way, for anyone who's not familiar with that, my advice to you, be very familiar with this number, that E for steel equals 200 times 10 to the power of 3 MBA. We will use it a lot in structural design, for steel design and concrete design. A lot, okay? I use it in millimeters to the power of 4, and L use it in millimeter, and pi is unitless, and that will give you your answer in Newton. If I need my answer in kilonewton, all I have to do here then times 10 to the power of negative 3. If I want my answer in kilonewtons, okay? So be careful. This here, if I want my answer in kilonewton, to change to kilonewton, divide by 1,000. Are we clear on units, guys? That's a very good session just to open your eyes on units. Where's Stella?
Yes, yes, all good.
Are we clear? The numbers that you are saying here, when they're using times 10 to the power of 9, I'm certain they are using different units around here. That's in meters. And then the problem with that, in Australia here, we use I in millimeter to the power of 4. In some other countries, they use it centimeter to the power of 4, which will be different values. So I'm telling you what we really widely use here in Australia, guys, okay? All the tables, you find the I value in millimeter to the power of 4.
Actually, my mistake was I was using the yielding stress they gave us, the 250 megapascal, straight away instead the E value. So for this reason, my result was
that's okay.
1,000 less.
That's okay. That's good. You made that mistake, so you remember it. All E value, it's always, most of the times, or not most of the times, in many cases, you won't be given E value. E for steel is always known to be 200 times 10 to the power of 3 megapascals. Okay, I'll show you some. These design capacity tables, where are they? Have I shown you this before? Guys, these are what we call them design capacity tables for, this is, you can get it on the internet, by the way, that's where I went to. Just search for that, for structural hollow sections. This is very similar to what you've got, but rather than the tables you've got for open sections, what we call them, this is for hollow sections. I'm not 100% sure if I showed you this before or not. And the reason I downloaded this to show you again, guys, why do we check the slenderness ratio? Because look at it, for a column, this is the design member capacity in axial compression. This is how much the capacity of a column for different columns, different shapes and different sizes. Look at it, from this portion to that portion, it's kind of linear. That's where Euler's equation apply. Before this portion, after this portion, start curving. Okay, and that's why, and that's for different columns too. In this area, you can say it's linear, very small area. Outside this area, we start being curves. That's where Euler's equations stop applying there, and we have, next semester, you will learn accurately how do we use these graphs, or rather than these graphs, we use these tables to calculate our column capacity. But just for you now to understand the basics of it, which is, it's a good exercise. We're learning how to make the units uniform, what material we're using, what strength, what I value, all of those variables that we don't want to get stuck with them, please, next semester. Those should be easy for you. So if I show you the design capacity or the property, section properties for those, the start, there we go. So the section properties for all these sections. At the start, and I think initially here. Modulus. There we go. Okay, guys, can you please have a quick look with me here? So properties of steel, telling you that all the steel that we are using in these tables has a Young's modulus of elasticity, or E, or we call it modulus, or elastic modulus, or modulus of elasticity, or Young's modulus, or the same name, 200 times 10 to the power 3 megapascals. This is the very common unit that we will use for all our calculations. The shear modulus, we will use that in some formulas. That would be 80, which is about 40% usually of the elastic modulus. Okay. The density of steel, the weight, if you need to calculate the weight of material, you've got about 7,850 kilograms per cubic meter. Poisson's ratio is 0.25. Anyway, those thermal expansion, those are not, you're not going to use them too much, but mainly, at least the first one is widely used. We will use it a lot in our calculations, okay? So please try to get used to, when we talk about elastic modulus, this is something given, known fact. when we talk, the same when I say steel, you know what steel is, you should straight away think steel has a modulus of elasticity of 200 times 10 to the power 3 megapascals. Okay? Like when you know the gravity acceleration 9.81, that's similar. Normal. That's the structural steel we use. And these are the different type of steel grades that we use with their yield strength and ultimate tensile strength values. Depends on the grade. When we say steel grade 350 or 450 or 250, these are the properties of dies. All good. These tables, by the way, you can find them online for free. For hollow sections, you find them for free. For open sections, you usually buy them, these books, and I would encourage you, if you'd like to invest, if you like structural design, invest in yourself for the future. It's about $150, I think, that book for hollow sections, but has exactly the same tables. Very good design document that will help you to design steel and make things easier for you. Anyway, that's the topic, or that's the document for next semester, not now, but this is just to give you an evidence. I know what I'm talking about, please. Just use these units, trust me. Keep your units uniform. Wherever you choose, keep your units uniform. This is the only advice I give you. Okay, we'll have a break. I think it's about time just to have a quick break. Let's have a lunch break. We'll come back at 1:15. Any questions before we go to the break on this exercise that we did? I'll stop the recording here.